Continuing our discussion about quantitative data, I'm going to start talking about significant figures. So when we have a value, a quantitative value that comes out of an experiment or something, it can have one of two classifications. It can be an exact value or an inexact value. As the name implies, exact values are exact. When you write down that number, you are completely describing the real quantity. So if you ask something like how many students are in the class, you could count that number and you would get when you give a number that there are 22 students in the class, that is fully accurate. You don't have any lost information. Another example would be the definition that there are 2 cups in 1 pint. It is exactly 2 cups. It's not 2.1 or anything like that. Exactly. So counting is generally how we come up with exact numbers. Inexact numbers are close, but not completely accurate. So the number may be a little bit off because it was measured not perfectly. Also issues with rounding. Every measured numerical value is inexact. Calling a value inexact does not mean it's worthless or not useful. Every single number that is measured using a piece of equipment is inexact. It's just a fact of life. And what we're going to talk about is how we deal with this. It's not a problem. We just need to be aware of it and think about what our inexact numbers look like and how that affects the values we think we have. So let's see kind of this in action. So the example of a question that would have an exact number answer is how many eggs are in 1 dozen eggs. Inexact would be something along the lines of what is my kid's temperature? And the reason we can distinguish these, the exact one, that's based on the definition. So we can tell it's exact because the definition of 1 dozen is 12. Whereas what is my kid's temperature requires you use a thermometer to measure it. So that is going to be a measured value. That's how we could tell it is inexact. So this inexact number is rounded. When we say the temperature is 101, that's not exactly perfect. There is more information. There are additional digits past the decimal point that we're not representing. So 101.4, 3, 1, 8. Those digits keep going, and they can be anything, right? You could tell based off rounding or something the kind of possible values, but there still are values there. When you look at the exact number, it was just always zeros. It doesn't matter how many more digits after the decimal point you include, the value is always going to be 12 because it's just 12.0. It zeros all the way down. And that is what signifies being exact. For inexact, those numbers would keep changing. And the value that you're representing is varying a little bit at a time, right? It's getting smaller and smaller changes, but it is still technically changing. Now, the question in general is, does it matter, right? If your question is, does my kid have a fever? Once you see 101, you're done, right? You don't need these other digits. It is like, most thermometers show that that tens digit. That'd be reasonable, but you really don't need the 3, 1, and the 8. So yes, her temperature may be at that level of accuracy. You may really be what the temperature is, but it doesn't matter for what we are talking about. So that's why it's not a deal breaker that your number is inexact. You can still tell that this kid has a fever. It doesn't really necessarily matter what the millionth place after the decimal is for the temperature. For this context, there could be other contexts where you're trying to measure temperatures of, say, in a chemical lab, or say you're running like a large-scale chemical plant and you want to have really tight temperature control. That may be important. But in terms of does this kid have a fever, those aren't useful or necessary. So the idea of inexactness and how good your value is when you're measuring it depends on the equipment that you use to measure that value. So when you do an experiment, say you're measuring temperature, you could use, say, thermometer A, where we can see that there are marks for every degree. Okay, so you have a mark for every degree, and you can see that that allows you to make a measurement. If we instead look at, say, thermometer B, there are marks for every 1/10 of a degree. That is a higher level of resolution that allows us to make a more significant, a more meaningful measurement, right? If you're looking at here on, say, go back to thermometer A, we know that this value is between 29 and 30, and we can estimate one more digit. So we could say, thermometer A, the temperature is 29.2. If we instead use thermometer B, when we cut across, now we have more information because we're using a better thermometer, and we could say maybe it's 29.25, right? So we can get another digit that is meaningful. And we call these digits the significant figures, or sig figs for short. And what they correspond to, what they describe, are the actual values of the digit that are meaningful. These numbers are both inexact, so there are more values after these digits that we've written. But you don't have a piece, you haven't used a piece of equipment good enough to give a significant value for that. If you took thermometer A, right, and this line right here, and you just said like that's 29.2735, all those digits that you just have added on are totally random. I just made up numbers, right? And what we're saying is if you tried to use this thermometer A, to measure anything after the 2, you might as well just make them up. They are not significant. They are not meaningful. So when you're using a piece of equipment, you want to be mindful of what is the potential error, what is the potential rounding that I can do with this piece of equipment to measure a value. In general, we're going to deal a lot more with numbers that we are just given, okay, or numbers that we measure that we then want to process and make sure that we have the right number of significant figures. So when we're given a value or when we see information, we want to be able to take this quantitative value and figure out how many of those digits are significant. And it's going to be an algorithm. So we have a process of basically digits that are always significant, digits that are never significant, and digits that are sometimes significant. So we'll look at this example. Our first number is 0.003100500. Okay. So always significant are the non-zero digits. So 3, 1, and 5 are not zeros, so they are definitely significant. So we can see that all of the other rules are all about determining whether or not in the zeros are significant. So that is where all of the complication comes from. When we have digits that are non-zero, 1, 2, 3, 4, 5, 6, 7, 8, 9 in a number, those digits are significant. So zeros that are always significant are the zeros between non-zero values. So when I say between, I mean literally like in the middle of the number. So 31005. So the zeros there that are spacing out the 1 and the 5, those are significant. One of the ways that when we are talking about significant is, does that number matter? And does it imply values for the value of the actual, thing that you're measuring? And so the 3, 1, and 5 are certainly important. And when these zeros here are in the middle, what you're implying, the reason why they're significant is you're saying that you know that those values are not anything else. They are explicitly 0, right? You didn't just randomly tack on zeros. They're not guesses. Those digits are equal to 0. So never significant are zeros in the front of a number. These zeros out here, 0.00, not significant. The reason why they're not significant is you are just saying that this value is small. You aren't contributing any information as to what the actual value is. Numbers, okay, yeah, so there's that. Then let's look at the 20,400 to see, oh no, yeah, sometimes significant, sorry, zeros at the end of a number only if there's a decimal point. So here I have zeros at the end of a number and I have a decimal point in the number. So that's why those are significant. But the reasoning here is just like the zeros in the middle, you are explicitly saying these values are 0. The values of those digits are 0. These are not just kind of placeholders. They're not just in there to make the number a certain size. You are saying you know the value of those digits is 0. So now if we look at the 20,400, we can see that this is non-zero digits. The 0 in between non-zero digits is significant. There's no zeros in the front, but now we have trailing zeros. Okay, and so the zeros at the end of the number are not significant in this case because there's no decimal point. If you wanted to make them significant, you would need to put in a decimal. You can just write a decimal point right there afterwards. So how we would interpret this number as written is you're saying that this number is about 20,400, right? But it's not exactly 20,400. It could be 20,417 or 20,440 or 20,390. You are saying you don't know what these values are. The reason why they have to be zeros is to make the number big, but they are not necessary to convey the actual value. You need to get the right magnitude, but you don't know what it is. So there's about 20,400 of something, but it's not a count, it's not exact. You don't know what those digits, the value of those digits are that are zero, because you've just approximately counted something. You know, is it like the population of a town where, you know, it's going to fluctuate. You're not exactly sure what it is or something like that. So I want to look at some examples determining the number of significant figures in a number. 7.020. We can always start with our digits that are non-zero. Then we can see that I have a 0 in the middle. That's going to be always significant. So then the only question becomes this 0 at the end. When I see a decimal point, 0 at the end is significant. There are 4 sig figs in this value. 0.0086. 8 is significant. 6 is significant. So then I have the zeros in the front. Because they're in the front, those are never significant, I have 2 sig figs. 0405. 4 and 5 are significant. 0 in the middle is significant. 0 in the front is not. There are 3 sig figs. So this we can see, this makes sense why we wouldn't count that. This number is 405. It is not significant to say that there is just, all you're saying is this number is less than 1,000 by putting a 0 there, which is good information, but by calling it 405, you've already conveyed that information. So that's why we certainly don't count that as significant. And it's the same reason why we don't count those as significant. Those leading zeros aren't necessary for conveying the actual value. They just tell you it's not big, which is good, but it's not significant. 1.033, those are definitely significant. The 1 and the 3, the zeros in the middle, doesn't matter how many zeros in the middle, they're going to be significant. I got 4. 0.395, all significant. 0 in the front is not. This can be a real tricky one, just that single 0. We do not want to count that as significant. One thing to note, when you are representing a value in scientific notation, you maintain all of the sig figs. So for example, here, the 7.020, all 4 are significant figures. So you keep all of them when representing it in scientific notation. Similar, you know, you don't use, we can see that you don't use, these we said in the front weren't important and they don't show up in scientific notation. The 8.6 is significant. The 8.6 that we see right there, similarly 3.395 becomes 3.95, 405 becomes 4.05. All right, another video down, still looking for any questions on participation 6.2. Maybe the next video will have one, who knows, gotta watch and find out. See you then.